Yeah, so welcome everybody. So it's a pleasure to give the first tutorial here of this workshop, and so it's for me it's the first time to be here, and I was positively surprised how beautiful is this neighborhood. And today I will start with introducing you to magnetic skyrmions, and in particular what kind of features might arise in the quantum limit. So this is, I would like to advertise two works that we recently put on archive. One is together with the organizers, which will appear as a review in Modern Physics very soon. And secondly, there is a paper that we recently did with Soper-Son and my colleague Jörg Schmalian. Yeah, so let me start with the outline. So that's the plan of this presentation. So I will start very shortly with magnetic skyrmions on the classical level. So they are classical topological field configurations. And then I will basically take more or less the other opposite extreme limits of asking what are actually skyrmions in the context of quantum magnetism. And then most of the time, however, I will spend on the question whether we can also understand the quantum aspects of skyrmions on a semi-classical level. And in particular, I will point out that the topological dipole conservation law is quite important, and explain you what kind of consequences this means for the physics of quantum skyrmions. Yeah, so as this is a tutorial, please interrupt me at any time. This is partially meant to be pedagogical, so some slides are very heavy. But I think you should be able to follow it, and please interrupt me and ask questions. I should also have a look at the time. Yeah, good. So let me start with the topological aspect. Magnetic skyrmions are classical topological field configurations. So it's a topological solution. It's a solution of a field theory with a topological property, and the starting point is actually the order parameter manifold of a Heisenberg magnet. So essentially, we assume we have a Heisenberg magnet where the magnetization can point in any direction. So it spans essentially the two-sphere. So this is essentially representing the orientation of the local magnetization, and this can vary in space. And if it covers this whole sphere, then I have a topologically non-trivial configuration, and one such configuration I can obtain by stereographically mapping this sphere to the two planes. So I map the south pole to the center, the north pole to the rim, and then I get a two-dimensional configuration of a magnetization that essentially covers all the two-sphere of the order parameter manifold. And there is also a mathematical non-trivial homotopic group associated with that. But yeah, if you so this is pi2 s2 is the group of integers, which means I can actually label these configurations with a winding number, an integer winding number. So how can one calculate this winding number? So there is actually an expression. I have to do a two-dimensional integral over space over something that I will call in the following topological skyrmion density, which is nothing but the solid angle spanned by neighboring spins that are adjacent. So you see, this is essentially the area which is spanned by how the magnetization varies along x and y direction. And if I project it to n, this essentially describes me the solid angle. And if I integrate it over space, and it really covers the full two-dimensional sphere. So if I divide it by 4 pi, I should get an integer. So there is an intuitive geometrical interpretation of this winding number. And as we will see, this is not just a mathematical curiosity, but this really has some physical consequences in the sense that it also impacts the dynamics of, and also the quantum dynamics, essentially, of the skyrmion. So this is really something where topology and kinematics are strongly interconnected. Yeah, so on the classical level, these skyrmions have been intensively investigated over the last 15 years. And I will just flash you some of the results. I will not aim to give you a comprehensive overview, but there was a very, very intensive effort. So in particular, there are 2 systems where skyrmions have been identified experimentally. So one are magnetic multilayers, and in magnetic multilayers, they're naturally at an interface, the inversion symmetry is broken, and then it was pointed out by Albert Fert and Levy that there is a Dzierzynski-Moria interaction arising at the interface due to this lack of inversion symmetry, and this gives rise to this DMI interaction, which in turn is able to stabilize skyrmionic textures. So I will not go into detail in stabilization mechanisms, but that is one of the routes how you can actually get skyrmionic textures with the help of Dzierzynski-Moria interaction. Yeah, so here I'm just giving 2 examples. These are clever designs of magnetic multilayers involving iridium, cobalt, iron, platinum in a very clever fashion. And then you can even stabilize skyrmions at room temperature. Room temperature is actually there are in some sense this field of skyrmions has 2 interests. So one is the magnetic community who want to get them at room temperatures where they can use them for some spintronic applications or for some other memory applications. But then in this talk, I will basically focus on the other limits. So I would like to have them at low temperatures, it's basically at 0 temperature, to see some quantum coherence emerging with these topological textures. Yeah, so magnetic multilayers are one platform, but there is also bulk magnetic crystals where skyrmions have been found, and this is a list that I took from a presentation of Jonathan White. And here you see various materials that have a point group that lacks inversion, some of them at least. In particular, a famous one is manganese silicon. This has a tetrahedral point group. It's cubic, but this tetrahedral point group actually allows also, means it lacks inversion symmetry and allows a Dzierzynski-Moria interaction. And this gives rise to skyrmionic textures. And manganese silicon is a metal. But there are also other examples. So iron germanium is very similar. It's also metallic, but there's also in particular an insulator which has essentially the same crystal symmetry class and also is magnetic and shows skyrmions. Yeah. So on the classical level, there is a lot of information available. And also about the properties of skyrmions, there is a lot of information available, for example, about the dynamics. So it has been also studied very intensively, and all these features can be all understood essentially on the semi-classical level. So you don't need to invoke really quantum mechanics. So for example, well, at least on some level, so, for example, the excitation modes of skyrmions have been studied with magnetic resonance spectroscopy. So this was in 2012, for example. So if you have a skyrmion, there are 3 magnetic resonances, counterclockwise, clockwise, and breathing mode, which have been studied in various systems. Here I show one of the first studies by Onose et al., where you see here clearly this microwave resonance where a skyrmion is actually excited and with a very specific resonance condition. I also want to mention work with inelastic neutron scattering by Weber et al. Where magnetic resonance spectroscopy probes the excitation modes at 0 wave factor. Inelastic neutron scattering actually at much higher wave factors. This was very challenging, and however, at least there are various excitation modes which could not be resolved by neutron scattering, but overall the intensity spectrums could be explained by theory. This is recent work by Brion light scattering, where also other more excitation modes than these, only these 3 can be actually could be resolved. Famously, I should also mention how skyrmions interact with spin currents. So if you drive them by spin currents, you can move skyrmions around. This leads to a skyrmion Hall effect, and also if you have a 3-dimensional system, the skyrmions might extend into the 3rd direction with strings, and then you also have interesting nonlinear dynamics of these skyrmions strings. So there is a wealth of interesting phenomena which have been studied on the classical level, and these are just basically should serve as some examples. Good. So but here in this talk I would like to ask the question, well, what are the signatures of magnetic skyrmions in the quantum limit? Are there actually interesting quantum effects associated with skyrmions? And let me first review kind of an activity that is approach that problem from a very extreme limit in some sense. Basically, one can actually just study magnetic skyrmions in quantum magnetism, right? One can start with a quantum Hamiltonian with interactions that are known to stabilize skyrmions on the classical level, and ask the question whether the spin wave function has some skyrmionic content. So the first thing to realize is that the classical skyrmion configurations are not an eigenstate of the Hamiltonian. As you know, basically there are only very few exact eigenstates known for quantum Hamiltonians. In particular, also the Néel state of antiferromagnetic order is also not an eigenstate, and so this means there are a lot of quantum fluctuations actually associated and expected to renormalize the classical solution. And this is of course also true for skyrmions. And the first attack one could approach that problem is just to look at the full quantum problem. And the full quantum problem is hard to solve, but one way to do it is just to apply brute force numerics. So you can just look at very small system sizes and treat the quantum Hamiltonian numerically exactly. However, there is a challenge in that problem, because we know that the skyrmion, if you want to look for a skyrmion, it has a certain size, and this size, in order to see a kind of reasonable texture, the skyrmion size should at least be larger than the lattice spacing that you use to put your, to realize you discretize your quantum Hamiltonian. So of course this is an obvious, this is obvious. So you should have the limit that the skyrmion size should at least much larger than the lattice spacing. But on the other hand, also the skyrmion size, the skyrmion should fit into the small system. So this means also the linear system size should be much larger, or larger at least, or much larger than the skyrmion size. And this, in 2 dimensions, where the linear system size scales like square root of n, where n is the number of spins in your system, you should actually fulfill this constraint, which is quite challenging because the quantum Hamiltonian is difficult to treat, and this means you are actually limited to a small number of n's. Yeah. So various people, various groups have actually attacked this problem, and here I'm giving very kind of a very short overview. So if you want to if you want to learn more and have more details, I would actually refer to our review article where we explain this in more detail and give the proper references. Okay, so one numerical approach is just exact diagonalization for a spin 1/2 system. So you can just take the full quantum Hamiltonian with interactions that stabilize skyrmions and just do an exact diagonalization study. And there are various activities in this direction. So one of the first was Lohani in Achim's Roche groups, who looked at frustrated skyrmions, and they were able to diagonalize systems with 31 spins. And you see, this is actually already quite a large system size and allowed actually to look at least the property of one skyrmion in the system. There are other groups, Sotnikov et al. And Siegel, who also looked at system sizes on the order of 10 and 20. So this is basically one type of approach. The other type of approach is to use density matrix randomization group. This is an advanced method that, however, usually only gives access to the ground state. I mean, there are advanced versions that allow you to get more information, but usually you are restricted to the ground state. But the advantage is that you can treat larger system sizes. Yeah, and then you can look what this numerics is telling you, and whether you can actually recognize skyrmions from the ground state solution of the system. But however, if you have a spin wave eigenfunction, you can ask, well, how can I actually now detect the skyrmionic content? But how can I, see from the spin wave eigenfunction if there are some skyrmion, if there is a skyrmion in it? And the easiest thing you can start with is just to evaluate the expectation value of the local spin operator. Yeah, you just take the ground state eigenfunction and calculate the expectation value of the spin operator, and these are, for example, 2 examples what you might get. So this is an example. What I'm showing here. This is taken from the work of Haller. This is the group of Thomas Schmidt in Luxembourg that treated that problem with density matrix randomization group. And what I'm showing you here, or what this picture is showing, is essentially the expectation value of the local spin operator. And importantly, this was obtained by, using very specific boundary conditions. So they used open boundary conditions and essentially looked at Hamiltonian with Dzierżynski-Moria interaction. And then what they found is essentially it looks like what we would call, sorry, this is maybe the wrong picture. This is what we would call a Néel skyrmion. So it very much looks like a classical a classical configuration. However, the only difference is that the spin length might actually vary. So there is actually a quantum randomization of the spin length. So it's not normalized to 1, but actually varies across the texture. And and if there are, if there are regions where there are more stronger fluctuations, then the spin length is actually reduced more compared to other regions. So, so in this case, essentially, if you do that, if you just calculate the local spin operator, you actually recognize the skyrmion, but the spin length might a bit renormalized, but otherwise, essentially, it's well recognizable. This is another example where the situation is completely different. This is a skyrmion which is stabilized by frustration, also with certain boundary condition. And this is taken from this Lohani work. And what you should know is that if you have a skyrmion stabilized by frustration, there are more internal degrees of freedom. So essentially, the Dzierżynski-Moria interaction breaks explicitly the chirality of the system. In the frustrated system, the chirality is not explicitly broken, and so you have essentially fluctuations of chirality, of helicity. And these helicity fluctuations essentially wash out the skyrmionic structure in the expectation value of the spin operator. So this means if you calculate this expectation value, what you get is something like that, which doesn't look like a skyrmion at all. So it essentially looks like more as a spin density wave, right? So this means if you just look at the local spin operator, this is not a guarantee that you can actually recognize whether the system has a skyrmionic content or not. Good. What else can you do? I told you in the first slide that there is a kind of a winding number. So there is on the classical level, there is a kind of a topologically quantized winding number that you can calculate. So this is depicted here again. So on the classical level, you can do this integral for the continuum theory. This is the topological density. If you integrate it, you get a number. So you can ask the question, is there something actually also available for quantum skyrmions? And there are two challenges now. Because usually if you treat the quantum problem, you treat it on the lattice. So this means you should first ask the question, can I channelize that object onto a lattice? So this is for the continuum, but can I do it for discrete lattice? And this question was asked many years ago, and here is and Berg and Lüscher gave an answer that you can actually calculate that Q or W, depending on the literature. Sometimes this is called a topological charge with letter Q or winding number with letter V, W. So you can actually calculate that for a system on a lattice. And if you have classical spins then of size S, right, then this expression actually gives you also a quantized object. But as I will explain later on, this is not guaranteed for the quantum problem. What else you can do is actually to look at the so-called scalar spin chirality. So the scalar spin chirality is also a famous object in quantum magnetism, in particular for frustrated systems. And if you look at how the scalar spin chirality is defined, so it essentially looks at 3 spins on neighboring sites, on 3 neighboring sites. So you take actually 2 spins, take the cross product, and then take the scalar product, and then you get a scalar. For that reason, it's called a scalar spin chirality. And if you look at that expression and go to the continuum limit, then you realize that actually you automatically actually reproduce this topological density because in the continuum limit, if I and j are on the same side, this combination will vanish. But so this means there should be at least on neighboring sites, and this gives you 2 gradients in the continuum approximation. So the scalar spin chirality in the continuum limit very naturally actually gives, reduces to the topological charge density. And so, so one way is just to calculate the expectation value of the scalar spin chirality operator. And this has been done by the various groups. So either look at this object or that object, and I don't want to go into details of these plots, but essentially what they are telling you, well, if you do that for quantum skyrmions, if you have these exact ground states of a quantum Hamiltonian with skyrmionic content, then looking at these objects might actually give you an indication that you have some skyrmionic features in the wave function, but doesn't really give you, they don't guarantee that you get actually a quantized winding number, because the quantum fluctuations will lead to renormalizations, and it's not quantized on the, it's not topologically quantized on the quantum level. Good. So this was one line of approach. Now just treating the full quantum problem. However, now let me take a step back and ask the question, well, let's ask basically a more modest question, and let us ask ourselves, can we quantize the magnetic skyrmions on a semi-classical level, right? Not solving the full quantum problem, but just basically start slowly and quantize it on a semi-classical level. So the idea is the following. At low energies, when we are not interested in all the kind of complicated high energy excitations of such a texture, then we could treat the skyrmion as a point particle with a position and momentum, and just replace their Poisson bracket with commutators, as we do in quantum mechanics. Right? Here I'm referring to a very nice review where this approach has been discussed by Ochoa and Zekovniak. However, if you want to approach, approach that problem, you first have to understand what's actually the momentum of a skyrmion, right? I mean, the position you can. You just basically identify this position of the skyrmion with some collective coordinate, but then you need to ask what's actually the linear momentum of a skyrmion. And this question is actually quite intricate, and it has also a very long history. So here I'm just basically citing a few works, some famous by Thiele in the 70s. Then there is famous work by Haldane in the 80s that asked the question, what is actually the linear momentum of a magnetic system? Wolovic, there is important work by Papanikolaou and Tomaras in the 90s, and there is also a very more recent work, and there is actually more, even more that I'm not added to this list. So let me now spend some time basically elaborating on that question. What is the momentum of a skyrmion, and in more general of magnetism? And before doing that, however, I have to introduce, momentum is a kind of a kinematic object. Before doing that, however, I want to introduce a geometric conservation law that is actually associated with the topological density. Because I promise the topological density is not just a mathematical curiosity, but it has some impact on the dynamics. And for that reason, we first need to understand how this topological density varies in time. If you take the time derivative of this object, then it turns out, because n, on the classical level, n is a unit vector, right? If you have a unit vector and you ask how the unit vector changes, it can only change in in the plane perpendicular to this unit vector, because it's a unit vector, so this means there is a restricted possibility how you can change a unit vector. It can only change in two directions. And this leads to a strong geometric constraint, which you can express in terms of a conservation law, of a continuity equation. So this means if you take the time derivative of this topological density, this means you take a third, you have already two derivatives, right? If you take a third, this means you can nicely reshuffle these derivatives and express it actually in a different way in terms of a divergence of a current, which we call a topological current. And this topological current is essentially a mixed derivative of space and time, right? So here you have another space derivative. So this means two space derivatives and one time derivative. The same here, one time derivative and two space derivatives. You just reshuffle them essentially, and you get the same thing. Yeah? So this has the form of a conservation law. And we will need this expression of the topological current in the following in order to understand actually what the linear momentum of a texture is. Okay, so now if we want to discuss kinematics, I have to tell you what is actually the equation of motion of a texture. And we have to first understand what is the classical field theory for magnetism, and the equation of motion is the Landau-Lifshitz equation on the classical level. So this means the time derivative of the local magnetization, the unit vector field, is given by a precession n cross an effective magnetic field that must be calculated from some energy functional. This is a functional derivative of some energy functional, which gives rise to an effective magnetic field in which the magnetization processes. The details of this energy functional is not important here, but we will assume that it's local for simplicity, so we neglect dipolar interactions, but we just assume that it's local for simplicity. So this equation of motion can be also phrased in terms of a Poisson bracket. This is the Poisson bracket where two magnetization vectors at different positions are essentially given by this expression. This is essentially a generalization of, it mimics the commutator of spins on the quantum level, right? So you have, if you remember how two spins commute, if they are on the same side, if they are on the same lattice side, then you get something which is essentially given by the antisymmetric tensor that mixes all these components. Okay, so and here I will just basically, look at this maybe academic question of just taking a pure magnetic system, not coupled to other degrees of freedom, no explicit damping, no extrinsic Gilbert damping, just looking at this field theory equation. And now I can ask, okay, what is now the linear momentum of that field theory? And this slide looks a little bit intimidating, but this is meant to be very pedagogical. So if you want to take away something from this talk, maybe it's this slide. So pay attention to it because it's not complicated. Yeah. So so let's start from the Landau-Lifshitz equation, right? So time derivative of n is n cross this functional derivative. So this is the starting equation. And now we do the following. We apply first an n cross operation, and then we multiply the derivative of n in a direction labeled by I. So this is a spatial derivative. So we apply this thing. If we apply it to the left-hand side, we just get this, right? So n cross applied to time derivative of n, then multiplied by the spatial derivative of n. So if we do the same operation on the right-hand side, So we first apply n cross, so there is this bucked subrule where we can simplify this expression, and then we apply the spatial derivative of n, then it turns out we just get this. So this is essentially the spatial derivative of n scalar product with this effective magnetic field. Okay? So now this expression simplifies for a translationally invariant theory. So if your theory does not break explicitly translation invariance, which we want to assume because we want to discuss the notion of linear momentum, which is only conserved for a translation invariant system, then this requires a little bit more computation, but it's actually a very easy exercise. Then you can write this product as a divergence of the stress tensor of the theory. Yeah? So this scalar product can be written as a divergence of sigma, where sigma is the stress tensor of the theory, now formulated in terms of the integrand of this energy functional, which I labeled as which is essentially the Hamiltonian. So this means just by doing this very simple exercise, this right-hand side can be expressed as a divergence. And if you look what this combination gives you, this is nothing but the topological current. It has two derivatives, one in space and one in time, and so this gives the topological current. So we arrive at this very nice looking equation that the topological current, you have to reshuffle a little bit the indices. For that reason, you have an antisymmetric tensor here. But in fact, you just have a topological current. There is a 4 pi because of normalization, and then there is the spin density because of this Landau-Lifshitz equation here. But essentially, you have a topological current which is given by the divergence of sigma. Okay. However, this is not in the form of a conservation law, right? We want to discuss the conservation law, so this means we expect a continuity equation. This is not the form of a continuity equation. So the question is what to do with that. And this is also why there has been a lot of discussions about the notion of linear momentum, because this is not a continuity equation. However, the trick is very simple. You can actually put that into the form of a continuity equation, but just massaging a little bit the left-hand side. And what we do is we use actually the continuity equation for the topological charge in order to reformulate to express the current in terms of space times time derivative of topological charge. So this trick is very similar. I mean, I was teaching electrodynamics to our bachelor students, and I was realizing, when one discusses, for example, the notion of a magnetic moment, one uses also microscopic currents, and then one massages the microscopic currents in terms of a dipole magnetic moment, and you use exactly the same manipulations there. Yeah. So now here we use the manipulations, however, for the topological current. So you see, you can just write the topological current as a derivative of space times the current. So this gives you two contributions by the product rule. If you apply the derivative to the position, you just recover the current, but then you get also another contribution which you have to subtract, right? If you apply the derivative on the current, this gives the divergence. But then you can actually replace the divergence with the time derivative of the density, because you have a continuity equation. And this simple manipulation actually allows you to rewrite this in terms of a proper continuity equation, where you have a time derivative of something plus a divergence of something equals 0, where P is now the linear momentum and big P, big pi, is the linear momentum current. Yes, please.
So I was wondering, so this should be, so if we think in terms of Noether's theorem?
Yes.
So then I also have a prescription of how to
Very good, yeah.
calculate
Yes.
the conserved quantities and also the continuity. So this should be equivalent. So if I follow the steps,
Exactly. Yes. You.
realize the invariance of the theory, the symmetries of the theory, and I follow these steps, I should recover.
Exactly. You recover this one. However, there is a caveat, which is also the origin of a lot of discussions. So, which I will not explain you here in this talk, because if you apply Noether, the procedure of Noether theorem, you need to start from a dynamic Lagrangian density, and the Landau-Lifshitz dynamics is formulated in terms of a Barry phase, which actually has a spin gauge symmetry. And if you do it naively, you will get actually a conservation law which is not spin gauge invariant. However, you can actually, because the continuity equation has some freedom, you can get rid of this spin gauge arbitrariness and formulate it in a manifestly spin gauge invariant form, which is exactly this one. Yeah, so it's not obvious, so you have to do a little bit of work, but you can actually formulate it exactly in this form. Yeah, so there is, you have to improve the continuity, you have to improve the energy momentum tensor in order to get this this form of conservation law. Yeah, so okay, so what do we get? So linear momentum by doing this procedure is given by topological charge times position. Right? This is what we get. And in particular, if you now integrate that for a closed system where there is no current leaving or entering the system, you get for the total linear momentum of a magnetic system this expression. Essentially, it's a prefactor times the first moment of topological charge. Yeah. So if you take the topological charge, multiply position, integrate it, the claim is that this is the linear momentum of the system. Yeah. So the claim is the momentum is nothing but the dipole moment of topological charge, and in particular for a closed system, the linear momentum is conserved, and this means also the topological dipole of a skyrmion is conserved. So there is a topological dipole conservation law. Okay. Yeah. So let's. Well, is there? So this is, you know, one can ask the question: is there some underlying mathematical structure which actually gives rise to that topological dipole conservation law? And the answer, yes, there is. And the next slide is a little bit more challenging. But at least I want, you know, you don't need to follow all these formulas, but at least I want to actually flash some keywords that are important in this context. And the keyword is area-preserving diffeomorphisms. So what is that? That is essentially a local transformation of the field theory that you know, you transform space locally such that that the area is preserved, so you don't stretch the system. Yeah, so this is local. This is area preserving. Diffeomorphism means just a mapping from space to space. And why is this? Why is this of, you know, of relevance? Well, if you we introduce the Poisson bracket of two field configurations, two fields. Well, fields at different positions. which is just this, right? So this is just a Poisson bracket that recovers the Landau-Lifshitz equation. So now we can ask the question, well, what is the Poisson bracket of the topological density? Yeah, topological density is that. If you calculated the Poisson bracket of topological density at position x with the field at position x prime, it's not a difficult exercise. You get an expression which looks like this. So there is a delta function, but now you have a derivative of this delta function, and you multiply also the derivative of the field. So what does this mean? This expression means that the topological density is the generator of area-preserving diffeomorphisms. So this means the topological density actually generates a local transformation which has the property that it doesn't change the area. So how can we see that? So let's look at the Poisson bracket of topological density. This is just a factor which I added here for convenience. So this is just topological density at position x prime with the field at x. And now I multiply it with an arbitrary function, completely arbitrary as a function of x prime, and integrate over x prime. And then I use that Poisson bracket, and then because of this delta function, I get rid of this integral, and what I'm left with is just this expression, which where psi is a local transformation. This is if you transform position locally with an infinitesimal transformation, you can actually do a Taylor expansion, and then in first order you just get this, where psi is this transformation, the shift of space, right? And if you look at this expression, then this psi has, however, this form. So it's given by an antisymmetric derivative of this scalar function, right? So this is a local transformation, and now this has the structure that it's area preserving in the sense that the divergence actually vanishes. Yeah, so because of this epsilon, of this antisymmetric structure. So as I said, you don't need to remember the details, but the keyword is actually area-preserving diffeomorphisms, and this is essentially a keyword because it's very important in the physics of the quantum Hall effect. So if you apply that now to the energy functional itself, you can actually derive, for the energy functional itself, you use a simple kind of rules that we have seen before. What you get is essentially that the topological density, the time derivative of the topological density is given by a double derivative of the stress tensor of the theory. So if you look at the time derivative of the topological density, this is given by a double derivative of the stress tensor. But this you have seen before in some sense, because I argued that the topological density obeys a continuity equation with the topological current. And I also told you that the topological current can be expressed as a divergence of the stress tensor. And this is just a combination of the two. Yeah? This formula was first derived by Papadikoula and Tomaras at the beginning of the 90s. And I think this result is not much appreciated in the literature, but it's very fundamental for magnetic textures. So in particular, it has the form of a dipole conservation law. So in particular, if you integrate that with benign boundary conditions, if you assume that the surface terms here vanish on the boundary, then you get actually two conservation laws. One is for the topological charge. This is good because topological charge is on the classical level meant to be a quantized integer, so it better does not fluctuate, right? But But you got also a conservation law for the topological dipole, which I denoted here by D, right? So essentially we just recover what I've told you before. Topological dipole is nothing but the linear momentum. It's conserved. So this means there is a dipole conservation law in the system. Okay, conservation laws of that type, where the current itself can be expressed as a divergence, became very fashionable actually recently, and are now discussed in the context of fracton matter. So what are fractons? So fractons is a concept that has first surfaced in the context of some exotic spin liquid models, and essentially it's a here I'm quoting here the review of Kromov and Radzichowski, which is a colloquium fracton matter. So if you want to learn more about it, please have a look at this review of modern physics article, where this sentence is taken from that article from the abstract. It's a class of models where quasi-particles are strictly immobile or display restricted mobility. I will explain what this means actually for our skyrmions. And it's known that fracton matter exhibits a lot of exotic phenomena like anomalous hydrodynamics, some ergodicity breaking, anomalous thermalizations, processes, and so on. And interestingly, what I'm claiming here, that magnetic textures is actually a playground for studying fracton matter. This has also not been appreciated. So if you read that colloquium, so they are saying there is an experimental void because there's all these nice phenomena. However, there is no experimental system really where this can be studied. But I'm saying, well, just look at skyrmion materials. They should actually, in some limit, behave as fractons and fracton matter. Okay, what does this mean? So I told you that well, the topological dipole. This is defined in this way, right? So you have a topological density, you multiply it by position, and then you integrate it. However, if you have a skyrmion, the topological density is expected to be localized around the skyrmion, right? So in this example, for example, here the topological density should be 0 because the spins do not vary. So the topological density should be somehow concentrated here in this area. And so this topological dipole should be a measure for a collective coordinate that tells you where the skyrmion is. So let's define a collective coordinate in that manner. Take the weighted topological dipole. So we just weight it by just for convenience, we weight it by the total topological charge, which is just an integer, but it just looks nicer, right? So and take that as a collective coordinate. Then the dipole conservation law enforces the following equation. So it's just basically, now what I'm saying, this is just the conservation of the total linear momentum. If I'm looking how it is defined, its linear momentum is essentially the dipole moment. And if I want to express it in terms of the collective coordinate, I can express it in this way. And this equation is nothing but the massless Thiele equation. So if you are familiar with skyrmions, you have encountered this effective equation of motion, which was derived by Thiele in the 70s. And in the absence of Gilbert damping, this just has this form. So it just basically is a reformulation of the conservation of linear momentum. Yeah, so what does this mean? It means the conservation of linear momentum means that this collective coordinate is constant in time. So this means the skyrmion does not move. It's immobile. And this is exactly what a fracton is. It does not move. It cannot move because the conservation law actually prohibits it to move around So it's an immobile particle as long as you do not break translation invariance. So if you break translation invariance, then you break, of course, linear momentum conservation, and then you can actually make the skyrmions move. But if you have a translation invariant system, conservation law implies skyrmion just does not move. It's a fracton. Good. Let me go one step further and now look at the Poisson algebra of the topological density itself. This is also quite interesting. So now we ask the question, what is actually the Poisson bracket of the topological density with the topological density at different positions? And this is also an easy exercise. And what you find is that this algebra is closed. So it can be expressed in terms of the topological density itself. It has a very similar structure as we have seen before. And this algebra is actually known from quantum Hall physics. And it's known as the Gerwin-McDonald-Platzmann algebra. And in the context of quantum Hall, this is the algebra that is fulfilled by the electron density. So if you replace the topological density with the electron density in the context of quantum Hall and project it to the lowest lambda level, you find actually that it fulfills the exact same algebra. This is responsible, for example, for charge neutral excitations in the fractional quantum Hall state. So there is a very deep connection actually between the dynamics of topological textures and quantum Hall physics. So if you now integrate that, if you multiply by x and multiply by x prime, integrate it over space twice, then you get actually the Poisson bracket of the dipole of the two dipole moments, and you find that if you do that exercise, that the right-hand side does not vanish, provided that you have a topological texture with finite topological charge. So this means if you have a skyrmion in a system with finite topological charge, the two components of the dipole moment do not commute. I mean, they have a vanishing Poisson bracket. So this means this is basically bringing us towards our goal of semi-classical quantization. So if you now say, okay, let's treat the collective coordinate, identifying that as the first moment of topological charge. Then we get a Poisson bracket between the collective coordinates, which is finite for a system with finite topological charge. And then we can quantize it now by going to commutators. So we get a commutator of the two positions, which is essentially IH bar times this expression. And this is essentially what one gets on the semi-classical level if one quantizes skyrmions in the low energy limit. And this structure actually constrains already the form of the effective quantum theory for the collective coordinates, because it should have this structure. So essentially, the conjugate variable to the position is the position itself. Yeah. So they are the two positions do not commute. So x and y position of the skyrmion do not commute. So they are conjugate variables. Or in other words, so x is the momentum, the linear momentum to y and to the y position and vice versa. And this is an effective theory that is actually follows from that structure. And of course, something like that has been written down already by Michael Stone in the 90s. But it's basically all adding up and is consistent with the conservation laws that you have in the system. Okay, how much time do you have?
You can conclude.
I can conclude?
Yeah.
Okay.
So we have more time for questions.
Yeah, wonderful. Good. I have one small section more that I will skip. I will just tell you what it is about. So one can now ask the question, well, okay, is this, I discussed everything on the classical level. Now you can ask the question, is this algebraic structure actually robust with respect to quantum fluctuations, right? And in this paper, we did some effort to argue, to show that this dipole conservation law is actually also holds on the quantum level, so that there are no quantum anomalies destroying this conservation law. And if you want to learn more about it, please have a look at that paper. And I have some more slides where I show that on, in the framework of a linear spin wave theory. But this I will skip, and I will jump to the end. First, I would like to acknowledge my collaborators. So I mentioned that we finished just recently this review together with some of the organizers. And please have a look here at this archive paper. It will shortly appear in RMP. And some of the work that I presented is also summarized in this archive paper, which was done in collaboration with Sopek Zorn and my colleague Jörg Schmaljan. And this is the summary. So in particular, I want to remind you that there is a very interesting algebra of the topological charge density, which is known from quantum Hall systems, and there should be a very close connection to the quantum Hall physics. The topological charge density is the generator of area-preserving diffeomorphisms and obeys the dipole conservation law. And for that reason, there is actually a close relation to the physics of fracton matter. In particular, the topological dipole of a single skyrmion is conserved. And for that reason, the topological dipole obeys a Thiele equation, a massless Thiele equation in the absence of some external damping mechanisms. Thank you very much for your attention.